Hey, what's up everybody? This tutorial is going to cover significance tests for a population mean. I'm going to run through the four-step process I like to use for these types of problems, and then we're going to look at an example, and I'll apply those 4 steps to the example. All right, here we go. I'll start with the 4 steps. In step 1, I always like to identify the parameter of interest, and then you're going to write your null and alternate hypotheses. So you go ahead and define what mu is. So here we're testing a population mean. So you're going to be defining mu, and then you're going to be making a hypothesis about that mu value. So remember, with your null hypothesis, mu is always going to get an equal sign. So mu equals some hypothesized value. Then your alternate hypothesis, you have one of 3 options. You have either greater than that same hypothesized value you did there, less than that hypothesized value, or not equal to that hypothesized value. So greater than alternate hypothesis is called an upper-tailed test. A less than alternate hypothesis is a lower-tailed test, and a not equal to is a two-tailed test. All right, step 2, you're going to verify your conditions and you're going to name your procedures. So there's really 3 conditions. You have a random condition, a normal condition, and an independence condition. So you always do have to have a random sample. For the normal sampling distribution, there's really 2 ways of checking for that. Either your sample size is large enough, n is greater than or equal to 30, or the problem will tell you about it having a normal population distribution. And then kind of a third way to do it is if you have the data set and you don't know if the population is normal and your sample size isn't sufficiently large, you can check a box plot. Usually what I look for in the box plot is symmetry and no outliers. And that will kind of get that second condition met. And then the third condition is the independence condition. The sample size should be no more than 10% of the population size. Then when you're going to name your procedure, you're either going to be using a z-test for mu or a t-test for mu. And I'll explain that in a sec. All right, then moving on to step 3 is where you actually carry out the hypothesis or the significance test. I'll start with what's called the z-test for mu. The z-test for mu is when sigma is known. So if you know that population standard deviation, this is when you're going to use the z statistic and perform the z-test. So once you've identified that you are doing the z-test, you're going to calculate the z-score. So it's x bar minus your hypothesized mu value, and that's the number that comes from your null hypothesis. You're going to then divide by the standard error. So the standard error is sigma over the square root of n. So make sure you get that square root of n over in there. Once you have the z-score, then you're going to calculate the p-value using the normal CDF TI calculator function. All right, so that's the procedure for step 3. The second case is where sigma is unknown. So this is what's usually going to happen is in practice is you don't know the population standard deviation. So what you're going to use instead is you're going to use the sample standard deviation. If you're using the sample standard deviation abbreviated as S, that's when you're going to use this t-test. So the t-test uses the t statistic, very similar to a z-score. You take the x bar value minus that hypothesized mu, but now what you're doing is you're dividing by s over the square root of n. So remember, we're using t when we're using s instead of sigma. Once you have that t statistic, you want to calculate a p-value. The p-value is using the tcdf TI calculator function. You have to, though, use the degrees of freedom. The degrees of freedom formula for this type of problem is just the sample size minus 1, so n minus 1, so pretty easy calculation there. So once you have that p-value, in either case, the z-test or the t-test, you're then going to do step 4. You're going to interpret the results in the context of the problem. So the 2 conclusions that you can have in this type of hypothesis test is either reject the null or fail to reject the null. You reject the null anytime the p-value is less than alpha, your significance level. Or you're going to fail to reject if you have a larger p-value, so if the p-value is greater than alpha. If you reject the null, then there is significant evidence for the alternate hypothesis. You want to put that in context. Or if you fail to reject, there's not significant evidence. All right, so let's apply that to an example. All right, I'll read the example, and then I'll work through it. So many consumers pay attention to stated nutritional contents on packaged foods when making purchases. Therefore, it's important that the information on the package be accurate. A random sample of 12 frozen dinners was selected, and the calorie content of each one was determined. The box reported that the calorie content was 240. Do the following data provide evidence to suggest the calorie content might be higher? All right, then what we have here is 12 data values that we're going to use to perform this hypothesis test or significance test. All right, so usually before I even start the first step, I want to write down the stuff that I'm given in the problem. So I know that I have an n value of 12, so n equals 12. And I know I'm going to have an x bar value. I'm going to have to calculate that. And in this case, I'm provided a sample. I don't know anything about the population standard deviation, so I know I'm going to have an S value. So these then I need to calculate. So I'm going to go ahead and put these into a list on my calculator. And I have this already here. So notice they're in my L1. So now I'm just going to do 1var stats. So stat calc 1var stats L1 and calculate. So I'm going to use my x bar value and my s value. So x bar is 244.333, s is 12.383. So again, make sure you're using s from this screen and not sigma. All right, so x bar is 244.333. S is 12.383. Okay, and the other thing here is it doesn't give me an alpha value. If you're not provided an alpha value, you can pick your own. Just for simplicity, I'm going to use a significance level of 5%. So 0.05 is what alpha is going to be. Okay, so now I can go ahead and move to step 1. So step 1, I'm going to start by defining my parameter of interest. So that's mu. So I just want to define what write down what mu means in this problem. So it's the true mean calorie content of this type of frozen dinner. Okay. So I defined what mu is. Now what I want to do is I want to write some hypotheses for mu. So I'm going to start with a null and an alternate. So my null hypothesis always gets an equal sign. So mu is going to equal 240. My alternate is, so I want to decide what I want to show as true about mu. So the box states that the calorie content was 240, so that was my null hypothesis, and I'm trying to show that whether or not the calorie content is actually higher than what they published. So my alternate hypothesis is that mu is going to be greater than 240. All right, so I'm going to be doing an upper tail test because I have that greater than alternate hypothesis. All right, so that's step 1. So I'm now going to move to step 2, where I test my verify my conditions and name my procedure. So I'm going to start by looking to make sure that this was a random sample, and it was. So I'm going to note that. So random sample, check. Now I'm going to look for my normal condition. So if I look back in the problem statement, it does not tell me that the population is normal. My n value is only 12, which is lower than that cutoff value of 30. But again, what I can do is if neither of those seem to be true, I can go ahead and make a box plot of my sample data. So I'm going to go ahead and do that. So I have the data in my calculator, so now I'm going to go to my stat plot. I'm going to turn on plot 1. I'm going to select the modified box plot, so the one that shows the outliers. Make sure that's in as L1. And then I'm going to do zoom stat to get a good look at the box plot. So I can see this is very symmetric. It certainly doesn't have any outliers. And then if I do reference a calculator box plot, I also want to go ahead and draw that. So I'm just going to run through, I'm going to hit trace just to get that 5-number summary so that I can make a good picture. All right, so I'm going to go ahead and draw that box plot next. So straighten that out. 225. 250. So you can just give it a scale. My minimum was at 225. I'm going to put a mark there. 236 is about here. 244.5 is about here. 253 is about here. And the max was at 265, which is about here. So I'm going to go ahead and connect those. Okay, so it's kind of that's my box plot. All right, so then I need to describe what that shows me. So I want to draw it, but then also interpret it. So what I can say here is that the sample box plot shows no outliers. I'll say shows symmetry and no outliers. Which suggests that the population was likely normal. Okay, so that meets my second condition here. Third condition is that I need independence. So I'm looking to see whether my sample was no more than 10% of my population. So this is going to be clearly true. I only sampled 12 frozen dinners. So if the population were 10 times larger than that, that would be 120 frozen dinners. You're certainly going to have way more than that when we're talking about food production here. So we'll say that over here the sample n equals 12 is much less than 10% of the population size. All right, so third condition met. So now I can just name my procedure. I'll say the conditions for a t-test for mu are met. Okay, so that is step 2. Kind of a lot, but manageable, I think. All right, so we're gonna move on to step 3. All right, step 3. So we're gonna want our test statistic, so our p-value. I also like to do my picture in this step. So to set up my picture, I need the mean of the sampling distribution and the standard error. So the mean is just going to be the same as what was hypothesized in step 1. The standard error can be approximated using the formula S over root n. So that was 12.383 over the square root of 12, which is about 1.212. So that's my standard mean and standard error. So I'm going to go ahead and set up this distribution. Okay, so then this is X bar, and this is a T distribution, so that gets marked as T. I'm going to go ahead and center this at 240, and then I'm going to count by my standard error. All right, so this would be about 241.2, 242.4, going down to 38.8, oops, and 237.6. All right, and then I'm going to go ahead and mark my corresponding T values. All right, so then what I'm trying to do is I'm trying to place my sample mean of 244.33 on this distribution. So I can see that this is going to be pretty far here to the left. So if I extend my picture, it's probably going to be about there. So that's an X bar value of 244.333 is about there. And then it is an upper tail test, so I want to shade to the right. So this is going to be the region that's going to represent my p-value. All right, so my next step then is to calculate my t, so my t statistic. So t in this case is going to equal, let me get back on black. So t is going to equal 244.333 minus 240 over my standard error. And that t is going to come out to be 3.575 about. Okay, and that matches up with my picture pretty well. It's certainly past 2 standard errors. Okay, last step I'm going to do is my p-value. So my p-value, I want to use TCDF on the calculator function. I can go and do that quick. So I'm going to go second vars, TCDF, and I'm going to just go ahead and sometimes it'll give you lower, upper. So my lower boundary is 3.575. My upper is unbounded, so I'm going to use a really large number by going 1E99. Then you also need to put in your degrees of freedom. So in this case we have a sample size of 12, so I'm going to have 11 degrees of freedom. So if you want to hit enter there, you get a p-value pretty small, 0.0022. All right, so this is going to be, so my p-value is 0.0022. So that then is the end of step 3. So then I want to move on to step 4, where I compare that p-value to alpha. So my p-value equals 0.0022, which is much less than that alpha value of 0.5. All right, so my conclusion then is to reject the null. So if I reject the null, so my null hypothesis was that that true mean calorie content was equal to 240, so the advertised value. If I'm rejecting that, then I have evidence for my alternate that mu is actually greater than 240. So then if we make that interpretation in context, I would say there is significant evidence to conclude that the mean caloric content of these frozen dinners is greater than 240. So again, we do have evidence for the alternate hypothesis, so we can say that we have evidence that caloric content is higher than the posted 240 calories. All right, so that is my 4-step process for the, in this case, a t-test for mu. All right, thanks for watching.